morning, good evening, everyone at the different places in the world. Yes, and today we will open this 24th International Multi-Phase Flow Technology Forum. And we were happy to invite Professor Frank Radjai from University of Montpellier. And today, I'd like to introduce the professor first. Professor Frank get his master degree in 1992 and a PhD degree in 1995 from the Paris Sala University at France. And after that, he worked as a postdoc research fellow at the University of Denmark in Germany. And after that, he worked as a junior researcher from 1997 to 2005 at CNRS at France. And after that, he got a research director of this CNRS at France until now. And for his Professor Frank Radjai's research, he has many publications in good quality papers, journals. For example, the Journal Rheology, Nature Communications, Journal of Engineering Mechanics, Physical Review Letters, Journal of Flow Mechanics, Physical Review Yeast, and so on. Today, Professor Frank Radjai will give us a topic is the particle fracture in granular materials by particle dynamic simulations. So welcome, Professor Frank Radjai.
Thank you very much. Thank you, Professor Yao, for this invitation. And it's a great pleasure to talk to your community, IMFTF. And I hope that this talk will be in line with what people of your community are interested in. And of course, I also seize this opportunity to say Happy New Year to everyone. So let me share. I think I can share. Professor Yao, may I share my screen?
Yeah. Wait a moment. I asked my colleague to help do this. Maybe,
yes, thank you.
Maybe you know, yeah. Yes, wait a moment.
Okay. Yeah.
Recording in progress.
Okay. So this will be about particle fracture in granular materials using particle dynamic simulations, and of course this is a very broad topic with many applications in different fields, not only in powder technology but also in soil mechanics and in many other examples of granular materials. And this is a process, the fragmentation of particles in general is a multi-scale process. At the packing scale, so at the scale of a granular material with many particles, of course, we have an inhomogeneous microstructure and force transmission. And so the force chains play an important role in the way the particles break. Then at the very scale of a single particle, we have joint effects of texture, mineralogy, morphology of the particle. So it's not sure that we can apply the same procedure of fragmentation to all types of particles. So we have a broad, also a field of different types of phenomenology for single particle fracture. At lower scales, so let's say at the micro scale and below, we have crack nucleation and propagation. This is a field in itself, and it involves effects such as disorder, defects, phases, and interfaces inside the materials. And even at lower scales, so at the atomic scale, we have, of course, also these concepts related to crystallography, such as weak planes, dislocations, and so on. So this is a very complex field in itself. And as far as we are concerned, when we study granular materials, we have also a broad list of different questions, such as effect of particle fragmentation on dynamics, rheology, flow of particles, how the particle sizes and shapes change, evolve during flow, how energy is dissipated, what's the variability, because by nature we have a big variability in the results, and the scaling with the system parameters, and of course also numerical modeling approaches, and in these approaches relevance of scales. So in the following, I will first briefly talk about different methods that can be used to model or even for experiments. Then I will give a small flavor of some of the studies that we have done for the investigation of breakage in granular materials. So cemented granular materials, grinding process in ball mills, single particle fracture mechanics, and evolution of grading curve during flow. And I will conclude with a few salient important points that we have to take into account when we study fragmentation. So regarding the methods, so now for a long time, it was very difficult to study the particle fracture in granular materials at the particle scale. Of course, we could measure the evolution of the particle size distribution by batch or by using other methods, but now using X-ray tomography, it's possible to study how particles break one by one. Here you see one example, which was done in Grenoble in France, where you can see a granular materials where the particles are breaking during compaction. So it is a very interesting, that opens very many interesting perspectives for validation of the modeling approaches, and also for studying really what is happening, as in this paper. For models of simulations of breakable particles, we can say we have at least four methods. So at the particle level approach, we can use DEM, discrete element method. And using them, we have also different methods, such as particle replacement methods, where when a particle breaks, we replace it by smaller particles. This is a very fast approach, or particle level approach, in the sense that when we replace really the broken particle by several smaller fragments, we have just to figure out which particles should replace the parent particle. It has a low computational cost because we're really not modeling what is happening during particle breakage. But it is, of course, highly dependent on the physics of particle fracture rules that we use for breakage. Then we have the fully continuum approaches. So we can, of course, implement in peridynamics, material point method, finite element method. fracture mechanics, so discontinuities inside continuum mechanics. And here, the advantage, of course, is that we can resolve internal stresses of the particles. So we can account for material behavior, but it has a very high computational cost. Here you see an example. We're using peridynamics. So I will not go into details of this method, but just in one sentence, peridynamics is discretization of the material on a grid using the integral form of the equations of motion. So it is a non-local approach. So here you see one example of a spherical particle, or let's say a spherical material, actually a spherical particle, but with defects inside. So these defects that you can see here as small segments can be distributed inside the material and subjected here, for example, to diametral compression. And as you can see, we can get, by using this continuum approach, which is rather fast as compared to FEM or other methods, the crack propagation and the fracture surfaces inside the material. This has been applied, for example, to study what's the effect of the distribution of disorder, the defects, the pre-cracks inside the material, and doing a large number of simulations and then doing statistics. For example, we can measure the threshold of breaking, the tensile strength of the particle, and see how it is distributed. Here you see an example of the survival probability of the particles under load. And as you can see, it can be very well fitted by a Weibull distribution, which is shown here. Sigma y is the threshold, is the breaking threshold, and sigma w is characteristic stress, and m is the Weibull modulus. Here it is 18 for the parameters that we used, which is very close to what we have, for example, for ceramics. Another method is lattice element method. So lattice element method is close to peridynamics, but it is simpler, so it is faster. So here you can see an example of tensile deformation of a cemented granular material. So I will come back to this example later below. So here, this is a multi-phase material. So we have both particles and the cementing binding material. We then can have hybrid approaches. So in hybrid approaches, typically we replace finite elements during fragmentation by discrete elements. So here you see an example of explosion. And as you can see, at the beginning, it's all continuum. And as fragments or discontinuities are generated, the finite elements are replaced by discrete elements. So it is faster typically when we can use both methods in a hybrid way. It can be faster than if we use only them. And of course, it is also more accurate at the beginning of the simulation. Here you see another example of hybrid peridynamics DEM, which was used recently. So peridynamics is used to resolve forces, stresses of the particles, and DEM is used to calculate the forces on the particles. We can use bonded particle methods. So this is more traditional, much more used during these last 20 years, where you just stick the particles together with some law, addition law, and then you can break these particles. Here you see an example, a 2D example of that. But here, of course, we resolve forces inside, but these forces are convoluted with disorder. So the stresses inside the particles are not continuous, they are discrete. And then we have the bonded cell method. This is the method that we have been using during these last years. in which we don't use spherical particles as in this bonded particle method, but polyhedra. I think now there are many more people who are trying to use this method in which we tessellate each particle into polyhedral particles as disordered as possible. I mean, should not be regular, but we can add some texture even when we tessellate. It resolves the internal stresses of the particles. Of course, we have to include the material behavior through the interface between the polyhedra inside each particle. And when we use these interfaces between particles, we have to apply the fracture mechanics rules. So here we have no loss of volume. The volume is conserved. We get generally well-defined fracture surfaces. And as I told you, we apply Griffith criterion to cell-cell interfaces. So typically we calculate, when we apply the Griffith criterion, we have to use it in a discrete form. So we assume that we have a toughness, a toughness of the material, which is G here, and we use the same rule based on energy, so the potential energy, and A is the surface area between two particles. And when the energy release rate is above this critical value of the energy release rate, the interface breaks. And that gives rise to a local form of the yield surface, as you can see here. So it can also be used as a yield surface, but it's better to use it point by point when we have an interface between two polyhedra rather than using a yield surface. But yield surface works also. So it's based on energy, but also we can have a threshold. So this method can be used both as a yield surface and as an energy-based criterion, which is shown here. So I will not go into the details. This work was done during the thesis of Luisa Orozco in Montpellier in 2019. So here you see an example of this method applied to vertical compression. The segments show the broken lines. This is in 2D. And you can see that we can get rather realistic fracture surfaces using this method. So we have analyzed these fracture lines. Here you see an example of biaxial shearing. Again, this was done several years ago. And as you can see, due to breakage and shear localization, we can get breakage of the particles mostly inside the shear bands. Okay, so let me go now to this two parts of my presentation where we have analyzed the data from simulations in order to get some rules for fragmentation. So for cemented granular materials first, because we have really validated and compared this method with some data and experiments. So an example, of course, this is in general, when we say cemented granular materials, we mean densely packed grains cemented together by a solid matrix. Here I show two examples, breccia. So this is a kind of rock, and wheat endosperm, and I will focus on wheat endosperm. So wheat endosperm is generally important for making powders, I mean flours for bread and pasta and so on. So it's important to characterize the grinding of the endosperm. Generally, I mean, traditionally, people characterize different types of wheats by looking at the distribution of the fragments generated. So, for example, here you see the distribution of fragment masses for a soft wheat and for a hard wheat. Generally, we have three types of wheat: soft, hard, and durum. Durum is rather hard. Vitreous, while soft is rather mealy, so it is a mealy texture. So it is important for the quality and the use of it. So here you see a close-up on the microstructure. So it is starch granules. So it's a granular materials. We have two types of starch granules of two different sizes, 20 micrometers and 5 micrometers. And the binding material is the protein matrix. So it's generally between 6 and 20%. And we have, of course, also voids inside the material. So the question that has not been well understood is which mechanical properties control the hardness of the material. We know the genetical origin. So the genetic origin of the hardness is in these proteins, which are called pyroindolines, A and B. And the amount of pyroindolines at the surface of the granules, starch granules, determines how much repulsion we have between the starch granules. So the more we have these pyroindolines at the surface, the lower is the adhesion between the granules. So genetically we know, but we don't know how this genetic property, genetic characteristics translate into mechanical behavior. That's what we studied. So for that, we use the lattice element method. So in lattice element method is a discretization of the material over a regular or non-regular disordered grid. And the mechanical behavior is encoded in the behavior of the 1D elements that join the nodes. So typically bars. So it can be springs or and so by correctly calibrating the material, we can produce let's say elastic brittle behavior, and we can control its elastic and rupture properties. So here, when we have several phases, like here in the wheat endosperm, we have particles, we have binding matrix and interfaces between. We can attribute different properties to the elements depending on where they are. So here you see 3 different types of phases: interface, particles, and the binding matrix, and all is discretized over a grid. And of course, the solution, it can be resolved either using, I think this is a video, yeah. You can solve it either in a quasi-static way, but you can also use a dynamic approach. So quasi-static resolution is faster. So here it is dynamic. As you can see, we can model rather complex behaviors. We guess that there are 2 properties which control the fracture of these materials. First, the adhesion between the matrix and the particles. So we call this sigma PM. So this is the strength of the interface, let's say. And another property is the amount, the volume of the binding matrix. So we have a volume behavior of the binding matrix. It's not only the behavior, its role as a binding matrix, binding particles together, but it has also some volume, and this volume, this phase can also transmit stresses. So we studied in a systematic way the role of these 2 parameters. So this is our parametric space. And here you see, for example, when we apply it to a volume element of the material, the tensile strength in simple tensile loading as a function of interface adhesion, sigma PM. P is for particle, M is for matrix. So you can see that for different amounts of the binding matrix, the strength increases with the adhesion. So in a way that you can see here in a nonlinear way. But we can, of course, scale the data. So there are ways to scale the data and produce from all these curves a single one. This is not the point of here. What I'm interested in is this curve and the next one. Here we have calculated the number of damaged particles. during tensile loading. And we have shown that actually the data for the number of damaged particles, which is something which can be measured in practice, is actually controlled by something which we call interface toughness. So we can define a toughness. So it is based on rupture mechanics concepts. And we find that in general, the toughness of the matrix. So it combines this toughness, the amount of the matrix, and also the adhesion. And both contribute to the toughness, and this toughness controls the damage of the particle. So it's interesting. And it is true both in quasi-static and in dynamic, because the grinding process is quite dynamic. The second interesting result is that if we look at the fraction of broken particles in this space, we see that we can differentiate different crack propagation patterns. So when we have, for example, low matrix volume fraction and low adhesion, then most of the time the cracks propagate bypass the particles. They propagate only in the binding matrix. But when one of these two, for example, when even at low volume fraction of the binding matrix, the adhesion is high, we get abrasion. So the cracks can also propagate into the particle, but they only chip the particle. They only break at the surface the particles, not they don't go deep inside the particles. And when both are high, we have crack propagation through both matrix and the binding matrix and the particles. So we were able to map this into the amount of pyroandolines by using the data from literature, and to propose that milli endosperm is characterized is this part of this in this phase, this part of the phase space, and the vitreous behavior is on the right side of the in this phase space. Then we did experiments. So for experiments, we used a way to control both the amount of the matrix and the adhesion. So by coating the particle using silicon. So by coating the particles, and of course the particles are expanded clay aggregates which break very easily. And we made samples with different values of the matrix and different So here I have one example of this, if you can see, which is broken, as you can see, under diametral compression. And so here also we have these three types of crack propagation. Below I have shown the three possible ways the cracks propagate. And here you see different modes, fracture modes. So we have, again, these three: high matrix volume fraction, weak adhesion, that breaks like this. Low matrix volume fraction, strong adhesion like this. And high matrix volume fraction, strong adhesion, we have this type of fraction. And we could count the number of particles that are broken or damaged. And we get from this data the same kind of phase space mapping. Okay. So I think I stop here for this part. It was already a bit long. And let me go to now particle dynamic simulations applied to different situations. So as I told you, we use what we call bonded cell method. Here is an example of simulations of a ball mill in which we use this Voronoi tessellation to transform particles into an assembly of fragments. And then we use fracture mechanics to break the particles. And as you see here, the particles which are broken are colored in black. And as it is rotating, we get more and more. It's a very long simulation, actually. And so I can show you what you get after many rotations. That gives ideas because, for example, here we see that most of the breakage is occurring on the left side, where the balls collide with the boundary and so on. And interesting is that although we can't have, because we are generating a large number of particles, and as you know, this is a weakness of the discrete element method, that we cannot handle a large number of particles when we do parametric studies. Of course, for a single simulation, we can use millions of particles. But when we do parametric studies, where we are interested to evaluate, investigate the effect of different parameters on the breakage here, we need to do many simulations. So basically, in general, for this work, we did thousands of simulations. So we can't have many particles, but still, even with a limited number of particles, we can have, by analyzing the data and evaluating the fluctuations, we can have rather well, very smooth data. Here you see, for example, the evolution of the average particle size, normalized here with the initial particle size for different rotation speeds. As you can see, they are very well defined. Or the surface generated, so the specific surface generated during grinding. So we studied, for example, the initial rate of surface generation. We changed different quantities which are important for grinding. Filling ratio, for example, this is the height of the material inside the rotating drum. The drum size as compared to the particle size. So we went here in this example from 16 to 66. And we see that it's not only the fruit number which is important. We have also these quantities which control the breakage. And in the end, by investigating all the effects, individual effects of these parameters, we were able to find a scaling parameter, gamma, which is shown here, in which S dot is the rate of surface generation compared to the initial value, and tau is a time, which depends on Cn, which is the strength of the particles, rho, their mass density, and G is the gravity. And a combination of fruit number, size ratio, and another ratio, which is the ratio actually of the weight of the particles to the strength of the particles. And with non-trivial exponents here, as you can see. And we can collapse all the data on a single line. This was done only for the cascading regime. So it is valid only for the cascading regime. When we leave this regime, this scaling doesn't work anymore. We also studied the evolution of, we have this population balance model, which is also a statistical approach to the grinding problem, in which we look at evolution of different classes of particle sizes. So we divided the sizes of the particles into 3 classes. And we looked at the rates of transition between these different classes. As you can see here, the evolution here, you have the evolution of the average sizes of the particles of these 3 classes. And here we have the rates, which have been evaluated from simulation. We show that we can model these rates by using these functions that you can see here. So we have basically 2 equations, but also we have the conservation of volume. And what is interesting here is that for this model, we had to include a term to account for the cushioning effect. So in a way, when you have a big particle, as you know, with many small particles around it, the stresses are not transmitted the same way as when you have a particle like here between a ball and the wall. So we have to account for the cushioning effect of smaller particles. And these are these terms which have been introduced here. No, sorry. Yeah, so and then we can fit. You can see this model can fit by choosing correctly these parameters. V is the volume, but these parameters alpha 1, alpha 2, and alpha 3, we can fit the data. For single particle fracture, we did a large number of simulations with two different methods. So the first method is the contact dynamics method. So in contact dynamics method, which is also a particle dynamics approach, we don't use elasticity at the contact point. We don't use spring dashboard model for the forces, but we use an implicit approach in which the forces are calculated as Lagrange multipliers. And here, these simulations have been done using the bonded cell method together with the contact dynamics. And we analyzed different quantities by using, of course, a large number of fragments, for a fine discretization of the particle, such as damage. So, for example, basically we have initial kinetic energy, which is the kinetic energy, impact energy, kinetic energy after failure, because the fragments can have a finite velocity after impact. We have dissipated energy and dissipated energy by fracture only, which depends on the fracture energy, GC, and the total surface energy generated, which is WS. So from these quantities, we can define the damage, which is the amount of surface generated compared to the initial surface. Fracture efficiency, which is how much of the eta is the fracture efficiency, how much of this energy is used for fracture, because the energy is also dissipated by inelastic collisions, by friction, and so on. And the restitution coefficient, which is the ratio of the energy, total energy, kinetic energy after breakage, and the impact energy, WK, which is this defines the square of the restitution coefficient. And here you see, for example, damage. So dW here, which was defined as the amount of surface generated for different values of fracture energy. As you can see, don't look much at the values of the fracture energy, because we have to look at this in a non-dimensional way. So it is mainly a parameter for us, which we change. But of course, it can be made realistic. It depends on the size of the particles that we consider. And as you can see here, for different values of the fracture energy, we have different dependence of this damage depending on the impact velocity. In the same way, the efficiency eta increases and then declines. So for an intermediate velocity here, which depends on GF, depends on the fracture energy, we have a maximum efficiency. For example, for GF equal to 2 joule per meter square, the peak is nearly 5 meter per second. So here, 30% of the total energy is used for fracture, which is low. I mean, only 30%, that's the highest value that we can get, is used for fracture. Otherwise it is dissipated. But we can here also scale the data. So if we use omega, which is the ratio of the initial energy to the total surface energy, the largest surface energy that you can get, I mean, the largest value of surface energy, we can use this omega. Yeah, yes. Yeah, if you use this parameter, you can see that the damage can be fitted by this, and all the data collapse on a single curve. Yeah, because I don't have much time, let's look at the restitution coefficient. we found that the restitution coefficient increases with this parameter omega all the time. In contact dynamic simulations, it is always increasing. So why increasing? Because as you see, for low values of omega, so basically, typically here we have small initial velocities. I mean, the impact velocities, all the energy is dissipated either for fracture or by inelastic collisions of the fragments. But as omega increases, the restitution coefficient is increasing because the kinetic energy is transported away by the fragments. So we have the excess energy, which is not used, part of the excess energy, which is not used for fracture, is carried away by the fragments. But later we did more simulations using this time the molecular dynamics approach or the smooth particle dynamics approach. We found that actually we have this more complex behavior. At low values of omega, we have elastic behavior. So we have rebound without fracture. And the restitution coefficient here is very close to 1 because we use also high restitution coefficient between fragments. Then we have a second regime where when omega increases in this range, the restitution coefficient is decreasing because we have more and more damage of the interfaces between the fragments inside the particle. So basically, we are damaging. So the damage is increasing. And then a third regime, and that's the regime that we saw before, where the restitution coefficient increases. And interesting point is that this quantity omega does not scale this third part. It only scales the first two parts of the behavior. And so that's interesting. And we find the same thing for agglomerates of wet particles, nearly the same behavior. Elastic, elastoplastic, and then damage and also fragmentation. So let me also add here that we studied recently the shapes of the fragments generated using a bounding box. So if you use the fragments and the bounding box with three dimensions A, B, and C, you can characterize either C over B or B over A as a function of omega, again, this parameter. And we see that we have actually C over B is generally very close to 1, or it's nearly close, nearly 0.9. This is also what is found in some experiments. But B over A, which is somehow the elongation of the particle, tends to a value which is about 0.7.
Recording stopped.
And we also found that the particle size distributions in the middle part, in the middle range of the values, because we don't have to consider very big fragments and very low fragments, where we have limits in this. These are the limits of the model because we can't go to very, very fine particles due to numerical efficiency. And we found, in general, that the particle masses have a power law distribution, as you can see here with a parameter tau, which has generally a value close to what we observe in many materials, something between 2 and 4. Okay, but we to finish, because I think now I have already, I think, at 43 minutes. We also studied the evolution of the particle size distribution during uniaxial consolidation. So this is less dynamic. It's like rather a quasi-static loading of the material, although the process itself is dynamic. So if we do it only in a strictly quasi-static way, we don't get the right results. So it's what is happening inside is rather quasi-static. And when we do this, so we are applying this method, we find features which are very similar to what we see in experiments. For example, here, we see that actually due to the cushioning effect, mostly. Most particles do not break. Many particles are only slightly damaged in uniaxial compaction. But we have shattering. So there are many places where we have particles which are fully broken. So this is very similar, for example, to what we see here. So this is nuclear fuel, UO2, uranium dioxide. And as the pressure is increasing, as you can see, at the beginning, you have fracture of a number of particles. Then we have shattering at some places. And as the pressure, confining pressure is increasing, we still have particles which are not fully broken. So we have this rather complex behavior. Here you see how the grading curve H as a function of size is evolving. So we start from a nearly monosize distribution. And as you can see, we generate particles of smaller and smaller size. And also we find a power law distribution of particle sizes here with an exponent 2.5. Okay, aspect ratio, we also find aspect ratio 0.7. I mean, this is the inverse of what we had before. It is also 0.7, the ratio of B over A, the parameter that I showed you before. So as we proceed, we are approaching more and more these limits. And I want just to remind that this distribution, I mean, this aspect ratio has been observed on lunar samples by Matsushima. And they explain it by saying that the property, this fragmentation process is a self-similar process. So we are in a state of self-similar fragmentation. We generate aspect ratios of 0.7. And the biaxial loading, we studied this under pressure. So it depends on the pressure applied again here. And the important result here is that, as you can see, as particles fracture more, so it basically for a material which you are shearing and where the particles do not break, you have here a peak value for the stress. So this is the shear stress normalized by the confining stress. And we have dilatancy, so the material dilates. I think everyone knows this property. But when the particles can break, and the more they can break, this dilatancy disappears. So we go from dilating behavior to a contracting behavior. So the peak also, the stress peak also disappears when the particles can break more. Okay, so I stop here. Let me just conclude with this slide, on which, because I started by telling you that this process of particle fragmentation is a complex process because it's a multi-scale process. And I want to relate this to the inefficiency of milling in the sense that it requires the energy cost is very high, the milling process. So there are three reasons, basically. First, because we have force chains, and I mentioned it before. So only particles which capture the strong force chains can break. The second effect is the cushioning effect, and that we showed using modeling that this is for grinding ball mills. In ball mills, it's a very important effect why the milling is not efficient. And the third one is that most of the strain energy is dissipated by contact interaction. So even single particle properties, fracture properties are important for grinding. It's not only because we have force chains, it's also because at lower scale, inside the particle and at the interactions between particle, we have this inelasticity of energy, and most of the energy is actually dissipated in general. Even when we have high restitution coefficient, is dissipated in interactions between particles. So let me stop here. Thank you very much for your attention.
Yeah. Thanks a lot for your presentation, Professor. And now, there's some actually, yeah, most question actually by me actually. Yeah, I asked some question for you. Yeah.
Yes.
Hello, Professor. Can you hear me?
Yes.
Yeah, sorry, because my. Oh, wait a moment.
I can hear you. There are some echoes.
Yes, I like to one by one. I like to give you the questions. The first question is, and do you have the experimenters to validate your simulation results, or your simulation is based on your experimental data, Professor?
Yes. Okay. Of course, I showed you one example of experimental validation for cemented granular materials. It's important, of course, to validate, or I would say more generally, it's important to quantify the uncertainties. It's more important. So even if we don't compare with experiments that we can do in our lab, we can always try to quantify the fluctuations, the variability, and uncertainties. And that's why parametric study is important. Sensitivity analysis or parametric study is important because that gives the trends. And it's much easier to determine the uncertainties when we study the trends rather than single parameter experiments. Most of time, validation is done on given system parameter. So we fix and so on. But in a really to get something, a very clear idea whether them is working or to validate a code or verify a code, I think it's important to do it during a parametric study. Yes, for binding materials, binded materials, we use for cemented materials, we use experiments to validate the behavior. And for them simulations, it's more difficult, but we have been trying always to compare with some existing experiments or yeah, reproducing an experiment is much more complex question because, of course, in industry, people try to reproduce experiments, so digital twins and so on are now. But I think there are many problems in them, so we have to be careful when we want to reproduce experiments. Sometimes you have to calibrate, but calibrate and this calibration doesn't work in another case. It's not good thing when it's not a general calibration. For this reason, yes, I think validation is essential, but I think now we are in a time. I showed you one example of experiments where of fragmentation at the particle scale where people use X-ray tomography, and I think that is really great because we can use them for validation.
Yes, you're right. I got you some work already done in your later the presentations. I found some pictures and some movies here. And the question from Professor Maitaba Kadiri, and he says that many thanks for highly informative talk on your simulations for the three regimes of single particle breakage. Why does the coefficient of restitution increase?
Yeah, why does yes. This is of course somehow paradoxical because we are in a state where we expect to have more dissipation and not larger restitution coefficient. Restitution coefficient is quantifying the ratio of the energy after and before the impact. It doesn't mean that there is less dissipation, because we are taking the ratio. So while we are increasing the impact energy, we have also more energy which is not dissipated. So we should see that like this. So dissipation is increasing, but the amount of dissipation which is not dissipated is increasing as compared to fracture energy. So fracture energy because we have a limit, and so the excess energy is either dissipated by inelastic collisions and friction or carried away by the particles, and that's what we see on the restitution coefficient, which increases because we have more excess energy, let's say.
Okay. And another question from my table gallery says that the new vertical lunar mirrors reduce their cautioning effects.
Yeah, I should comment on that. I should comment on that, Farhang. Yeah, the point of cushioning, reducing the efficiency of milling is really a big problem. And for example, for drum mills, I mean, they are very prone to that. So a company in Newcastle in England, they developed a vertical roller mill where the rollers were rolling on a vertical wall. And that when the particles were crushing, they were separating the fines. And we evaluated the efficiency, and it was remarkably very high efficiency. For some reason, the company went bankrupt. and then for a while, the technology was taken up by Hosokawa Micron for maintenance. But I'm pleased to see that the design, it has now been taken up by an Indian firm, and they are starting making these vertical mills. So your work on this cushioning actually points to a big problem that the industry is trying to address.
Okay, that's interesting. Yeah, to know that you can, I mean, because that what you're saying is very simple idea to say we remove the fines, and so it's interesting. Of course, if they are cohesive, it's difficult to remove. No, they should use some wind or something.
Yeah, indeed. If they're cohesive, then they pile up on the wall, and then you may need a scraper.
Okay.
Yeah.
Very interesting.
Okay.
Thank you.
Yeah, and another question from Professor Gui Lan at Tsinghua University. He says that it is interesting, and I want to know more about how to search the collision between sharp-angled particles.
Yes. Yeah, that is an interesting question. I didn't discuss this point. I was fast for when we tessellate particles into polyhedra, we have to treat the interfaces between polyhedra, and of course also when they break. Now between polyhedra we can have face, edge, different types of contacts, vertex surface, and so on. Generally, most people who use polyhedral particles and also in soft waves that you can find on the market, they use very simple contact laws or force laws, which consists in using the overlap volume between two polyhedra, the overlap volume as the strain parameter. So basically, the force is proportional to the overlap volume. I think this is not physically correct. I mean, clearly, it's not correct. Although it seems to work when you use over many steps, time steps, but we have to account for the geometrical constraints. So when we have two spheres, we have only one unilateral constraint between two particles. Basically, it is related to the overlap. But when we have a face contact, for example, we have at least three geometrical constraints. And so we have to account for these three, because the relative rotations between at an interface between two polyhedra requires at least three dynamic variables to control. So we cannot use only one quantity, which is the overlap volume, to solve forces. So that's what we do. We use three constraints at least for a contact, for face contact, and two constraints for an edge surface contact. So in a way, we are considering that a face contact is equivalent to 3-point contacts. And at each of these at least 3-point contacts, we implement, as usual, a force displacement relation. And so when we solve the three, then we can account for the relative motion of the two particles at the interface.
Okay, and thank God for Frank Radjai. Yes, presentation due to time limitations. So your presentation is stop here, and maybe some people outside of this Zoom have some questions. I will ask these people to write emails for your questions regarding your presentation.
Yes,
and
I will answer all questions by email and with pleasure, with greatest pleasure. And thank you again for this invitation.
Yeah.
And it was a pleasure to be online with you and all the community. Thank you.
Yeah, thank you very much, Frank. Yeah, I will connect with you later about something about this presentation. Yeah, and thank you a lot for my Gadiri for recommendation. This professor join us. Yeah,
thank you.
Thank you very much. Yeah.